I'm Ennemcien. We have seen that a molecule that does not have a dipole moment is called a non-polar molecule. When such a molecule is placed in an electric field, a displacement between positive and negative charges takes place and it acquires a dipole moment. A material made up of such non-polar molecules are called non-polar material. If a block of such a material is placed in an electric field, due to the polarization or due to the displacement of the positive and negative charges, a net charge appears on one face of the material and an opposite charge on the other face of the material. These are two parallel metal plates connected to a battery, so there is a uniform electric field in between the plates whose intensity is E0. When a non-polar dielectric material is placed inside the field, there is a net positive charge on this face and a net negative charge on this face due to polarization of the molecules of the material. As a result, we have seen earlier that intensity of electric field inside the material is reduced to sigma E equals sigma by epsilon 0 epsilon r. But sigma by epsilon 0 is E0, so that field inside the material is E0 by epsilon r. Epsilon r is the relative permittivity or dielectric constant, which is always greater than 1, so that E is less than E0. Thus, there is a reduction in the strength of electric field as the material is placed inside an external electric field. This reduction in field is also known as polarization. That is the effect of polarization. Now the intensity inside the material is reduced so that lines of force, number of lines of force inside the material is also reduced. See, this is reduced. Now, if the molecule or if the material is made up of molecules having their own dipole moment, even in the absence of an electric field, and when such a material is placed in an electric field, the dipoles get themselves parallel to the applied field direction. This also creates some sort of positive and negative charges on the opposite faces of the material. This is also polarization. And that result is the reduction in the intensity of electric field. Now, what is it? What is a dielectric and what is an insulator? In fact, dielectric is also an insulator, which does not have free electrons. And when such a material is placed in an electric field, polarization takes place, that is, shifting or displacement of positive and negative charges take place, and as a result, a net charge density appears on either face of the material. And field inside is reduced below the intensity of the applied field. A dielectric is one in which polarization occurs under the influence of moderate electric fields, that is, electric fields of moderate strength. But insulator is one in which polarization does not take place under the influence of moderate electric fields. It requires field of extremely high intensity. That's the difference between dielectric and insulator. Now, there is another class of material called conducting materials. In conducting materials, there are free electrons. These free electrons move at random inside the conducting body, just like gas molecules. But when such a material, conducting material, is placed inside an electric field, these electrons, free electrons, experience a net force and they move in the direction opposite to the applied field. And electrons accumulate on one face, leaving a net positive charge on the other face. See, this is the case. This is a conducting body in which free electrons move at random in the absence of an electric field. But when it is placed inside an electric field, the free electrons, under the influence of the applied field, move towards this face, producing a net negative charge density here and a positive charge density here. This is equivalent to a pair of equivalent oppositely charged plane sheets. These charges produce an additional electric field inside the material or conducting material, which is equal to the applied field in magnitude, but opposite in direction. The induced field is in this direction, whereas the applied field is in this direction. In metals, these two fields are equal in magnitude so that they cancel each other, and the intensity of field inside the conducting material reduces to zero. In a dielectric material, field intensity is not reduced to zero but reduced to a finite definite value given by E0 by epsilon r. Let's see difference in behavior between dielectric and insulator. Now the lines of force for a dielectric material are shown here. Number of lines of force is used to represent intensity of electric field. We have seen it earlier. Since intensity inside dielectric material is reduced, a number of lines of force are also reduced. See the difference. In between the or in this gap space, electric intensity is E0, but inside it is less than E0 and is equal to E0 by epsilon r. So the number of lines is less. But in metal field intensity inside is reduced to 0. So there are no lines of force need be drawn inside the conducting body. Now, at any point A in this gap, electric intensity is same as E0, the applied field. At any point B, well inside the metal, electric intensity is 0. In this gap, intensity is E0. At these points, intensity is 0 that we have seen earlier. Electric intensity outside a pair of parallel metal plates charged with equal and opposite charges is 0. So these are the nature of the lines of force when a metal is or a good conductor is conducting body is placed in an electric field. These lines, nature of these lines is the same regardless of shape of the material. It can be a sphere, rectangular block, etc. Now here is a doubt in connection with we have seen that intensity inside a dielectric is E equals E0 by epsilon r. So E is less than E0 by a factor 1 by epsilon r. If you apply this result to a conducting body, in a conducting body E equals 0 inside, that means epsilon r must be infinity. Is it so? No. Epsilon r or dielectric constant or relative permittivity of matter is not infinity because the process taking place in a dielectric material and conducting material, the processes taking place in a dielectric material and in a conducting material are entirely different. In dielectric material, a reduction in intensity is due to the phenomenon polarization. Inside a metal or conducting body, intensity is reduced to 0 by the movement of free electrons, where electric dipole has no meaning. And so there is no polarization. And so you cannot apply this formula for a metal body as it is. Now, you cannot apply same rule or same formula in two cases where processes are entirely different. Now, the dielectric constant depends on various factors. It varies, changes from material to material. It depends on the nature of the electric field, whether it is DC or constant, uniform, or whether it is oscillatory field. Such a field always changes in direction and magnitude. In such case, the electric constant behaves differently from what it is in a static electric field. Another point is, for every dielectric material, that there exists a limiting field intensity beyond which the dielectric loses its property and it behaves like a conductor. And this limiting field is called dielectric strength of the material. That is the maximum field that can be applied without losing dielectric property. And if the limit is exceeded, the dielectric will break down. Its properties are changed entirely. So, we have seen the difference between insulator dielectric and good conductor. Once again, a dielectric is an insulator in which polarization takes place even under the influence of or under the action of electric field of moderate strength. But in insulator, the molecules are tightly packed and energy values are such that polarization does not take place under the influence of normal or moderate electric field. It requires very strong field, that there is no perfect insulator for practical applications. Okay, thank you. We will see problems and conceptual questions in the coming postings. Thank you.